Yeah, I'm Tammy Arago,
Okay.
and they.
Roy. Danny Roy Algo.
Okay. And how did you find out about our group?
Well, went looking online and actually attended the general astronomy class.
Oh, okay.
He ran in last Sunday.
Okay, great. Well, welcome aboard. Hopefully it won't be your first and last visit with us, but, you know. And you are?
Don't know.
Okay. And
I'm trying to get. It's called the giant impact hypothesis, not impact theory. So, how Google impact theory? What kind of impact theory? Like genetic impact, physical impact.
an impact by any other name.
Oh, you're talking about the misprint on
Yes.
the information poster over there?
Yes.
Okay.
I can safely say that I had nothing to do with it.
One smart alike.
I've told him where to address the street.
Yes, yes.
One.
So anyway, again, welcome to February's meeting. Yeah, February already. Our guest speaker this evening is Dr. Collin Turley, and he's going to talk about how fast we can go. And my first question to him is, fast, is that an acronym for something? He said, nope, it's just going fast. So I don't know if he means ludicrous speed or not, but
Notorious speed.
okay. So, Dr. Turley.
Hello, everyone. I believe I gave a talk here probably about a year and a half-ish ago. I think I did it remotely because it just happened I got COVID just before I had to give my talk, which wonderful timing. I gave a talk on how space can kill you. Now I'm going to do a talk on how to go fast. So, also, why you might not want to. Because every action has consequences. Going fast has many.
Friction.
Among other things, yes. We'll get to things that are more ridiculous. So first of all, let's start off with step one of going anywhere. Step one of going anywhere is to do the simple things that we're good at. Namely, give me a moment because they actually do the thing with the stuff. It's on. Yes, it is. All right. First thing you can do is you can go somewhere on foot, aka walking a lot. And people are good at that. We're literally evolved to walk, but the problem is it's a lot of work, and it's really not that fast. You need to carry everything you want with you. So yes, you can get somewhere generally by walking. Actually, a very efficient way of doing it. I believe if you want to push the absolute limits of someone just getting somewhere on foot, there's people through hike the Appalachian Trail, which is going over difficult terrain on foot, carrying your own supplies everywhere. I think the record for doing the entire 1,000-mile trail over all the hills is about 45 days, which basically means you're effectively running 50 miles a day on basically mountain roads and over boulders, under trees. It's insane. But it's a lot of work, and most people can't do that. I can't do that. So running, it's fast, but it's not that fast. Let's go back. Okay, this thing is not fine. Let me see if I can adjust the thingy here. Take it out, put it back in. There we go. That's working better now. Now it actually works. Okay. So what if we accelerate? Yeah. The fastest way to move things around was by horse for human history. Problem with that's on walking, that's what they can carry cargo, but there's a lot of problems. One thing, horses get tired faster than we do. Actually, if you do human versus horse race, horses only win the race if you do a short distance race. If you start going like more than 20, 30 miles, people can start coming ahead, especially on a multi-day trip. Go far enough and you actually can outrun horses. It's just you can't do it on the short sprint. You have to do it on the ultra-marathon level. The ultra-marathon level, we beat horses. Problem, so that means if you want to get anywhere fast on the horse, you basically have to do the Pony Express method, where you get one horse, run the horse till it's exhausted, get another horse, rinse and repeat until you get somewhere else. The Pony Express could literally get a letter across this continent, this country, over a matter of like 10 days or so. But it was very expensive to maintain. You literally like change horses every 50, 60 miles or less, which is, and you do more people in the mountains, not that good. Also, say what? 25 miles, thank you. I didn't have the exact number, but it's pretty good.
From Missouri, St. Louis, Missouri to California.
That sounds about right. Yes.
And it costs the equivalent of $80 to send it over.
That is not good. That is, you can see that's expensive.
That's why they went big for
Yeah, only lasted 18 months. Anyway.
hard work.
Well, Well, as I said, well, the problem is that you have a lot of terrain limits. On foot, you can basically cover almost any terrain. Horses are more limited, and also they need a lot of upkeep. Horses, you have to feed them. Also, they poop everywhere.
They're living things.
They're living things, mostly. So let's go one step faster. All right, is this thing still not thingifying?
Thingifying.
Well, thing the thing.
It's not a word.
So it's a word. It's a wordification. We go word, we use it as a word to make the word worded. Please comprehend that if you don't comprehend that. Okay. So I prefer every perfectly cromulent. Yeah, perfectly cromulent word. Yeah, I think most linguists I know are descriptivists. They simply describe how language is used. If it words, it's a word, it's a word. Even if it shouldn't be worded that way. Okay, so let's go now one step forward. We can go to the center of the car. Cars are faster, and great. Cover distance at speed, you can carry your cargo. One problem. You need a road. A lot of road. And also, cars don't go that fast. At some point, it's faster. Your average average car person knows can't go too far, can't go that fast. I think most cars don't go too far above 100, 150, depending on how much power you have in your engine, and still not that efficient. Got some problems.
Well, there's the Bugatti Chiron Super Sport.
Still, you can go fast, but how long do you have to go before you put in more gas in the tank?
300 miles per hour.
That's not fast enough. So, how fast could you go if you push a car to the absolute limit? Well, the absolute limit of a car is basically the top fuel dragster. I should say this is a piston engine, because you can go faster if you put a jet engine in the car. If you want to limit yourself to a piston engine, dragster is the best bet. And these are pretty effective. They can go, they cover the 1,000-foot distance in about 3.6 seconds. They're very effective. Problem is, they literally only run 1,000 feet and then the engine stops working. They literally have to rebuild the engine after every single race. Also, they're so loud, you have to wear ear protection if you're after the races. You can feel the engine vibrating your lungs out of your chest. It's that loud. No questions?
Does the Bugatti Chiron Super Sport use that?
No. You can't use that engine because if you do, your engine runs for 1,000 feet and then you have to build a new one. The Bugatti, put it this way, if you take the Bugatti and you're going at 60 miles an hour in the Bugatti and you floor it at the moment past the dragster can start from a dead stop and pass you in a second or two. The top of the dragsters are insane with their acceleration. They can accelerate, they have an average acceleration that's about 3.5 to 4 Gs.
Well, the Bugatti Chiron Super Sport can go over 320 miles per hour.
This, once again, this will blow that thing's walls out. You're not going to, if you want to have acceleration, top fuel dragster is the absolute limit of what you can do with a piston engine. Anyway, one problem is that powering a car by the wheels is not effective above about 300 miles an hour. At that point, turning the wheels stops actually functioning for high speed. Above that, you really start to have significant losses, and powering yourself by wheel-based drives doesn't work too well. Also, stopping's a bit of a problem. Dragsters, their engines run so hard that once they get in the race, they actually can't turn the engine off. The engine will run under its own inertia and diesel such that it just runs and runs until it runs out of gas. Also, they don't have enough room for brakes. They put parachutes in the back of the car. They use parachute brakes to stop. So stopping is a bit of a problem. All right, let's go one step forward. What about a boat? Well, going fast in a boat is cool, but not a good idea. Because even the sled bump into the lake, and your boat is now no longer a boat, it's now a bunch of shrapnel. Literally, this is one of the most dangerous world records for ice heading. The most recent record was set in 1978, set a record of about 511 kilometers an hour on water. That's like 315 miles an hour, give or take. That's fast enough that every time someone tried to break that record, their boat hit the tiniest ripple in the pond and flipped over and disintegrated. They didn't find the body; they found basically shrapnel across a giant part of the lake. So yes, you can go fast in boats, but at some point your boats will mostly just hydroplaning and also powered by jet engines, which is, a bit of a problem. Also, you need a lake, and if there's any bumps, your boat's now shrapnel. And piloting shrapnel is not a good plan, because also you're shrapnel at the same time, and dying's not a good way to travel somewhere. Usually. So, onward and forward. What trains?
Trying to go through the entire diameter of Montenegro in an hour.
Bad idea. Now, trains Trains are great, and actually, if you have high-speed rail, you can go unimaginably fast. High-speed rail can go well over 200 miles an hour. But the problem is, you're going to go somewhere with those rails, and rails are expensive. But the best part about rails is that if you're on rails, the trip is actually quite smooth. If you're on a high-speed train, it feels really smooth. You almost don't notice you're going places sometimes. You can walk around and not feel like you're being bounced around like you are like a bus or a car.
Or the super trains, like, I don't know, like Japan.
Yep. All the problem is, the thing is, at higher speed, even literal physical iron rails get a bit bumpy and problematic.
What about the monorail?
So what monorails are usually not the best plan. If you want to go faster, you want to use a maglev train.
Oh, I've heard those.
Problem is, they're stupid expensive to build, and currently there's no, to my knowledge, no high-speed commercially viable maglev trains. There's a few in Japan that are mostly prototypes to test out, can you even do this, and can you do it so that in a way that doesn't break. I think their train, once it gets above a critical speed, it just floats over the rails, and they set a record there of about 375 miles per hour on this train, what you see right here. It goes ungodly fast, but once again, it's only the record of 375 miles per hour. And that's still, in the grand scheme of things, not that fast. I mean, you're only going a few hundred miles an hour, and you can only go over where you have magnetic rails built, and still, there's limits to this. Cool idea. So far, we're not even going that fast yet. So let's go faster. Well, next step up would be a jet-powered car. This is actually a picture of the fastest car ever built, and it is much faster. Problem is, it consumes fuel like crazy. It's basically a gas tank with some wheels attached and a bunch of engines. Also, once you're near the ground, you have a problem. The ground effect. Question? Not a question. There's a thing called the ground effect. Basically, when you push air out of the way, you create sort of a wave of air coming off you. When a boat goes like they say wake. You make a wake in the air too.
A street eagle car.
So you make a wake, and the thing is, if you're near the ground, that wake interacts with the ground, making more air resistance. So if you're near the ground, there's more air resistance than there is if you're up away from the ground. Similarly, if you're in an airplane and you get close to the ground, the ground effect provides a bit of reflection off the ground and keeps you floating. So over a runway, planes feel like they kind of float. And if you're not prepared for that, you can actually miss the runway because you float over it and don't land. So the ground effect is complicated when you're landing in an airplane, and for a car, it adds a lot of extra drag. So if you want to go super fast, you actually have problems. Now, currently, the fastest cars in the world are actually limited not by power, but by how much road they have before they run out of physical area to drive on. There's a lake bed they drive on somewhere in Africa that's like a dry up lake bed. The problem is they can only go so far because they run out of lake bed and have to stop. Because if you have any bumps in the road, you're screwed. A bump at 500 at the speed of sound is a death sentence. So they literally drive as far as they have road, and that road runs out eventually. So effectively they're limited not by how fast they can go, but rather by how much road they have before they hit something, which is a problem. Question.
Is that fast shot that can go straight to a tree?
I would not recommend going to a tree. If you went to a tree, you'd be dead. Also, the tree would be dead too. In fact, everything would also be on fire. But different problem. So yes, you could drive to a tree. No, you wouldn't survive the process. So as I tell my students in physics a lot of times, it's not that you can't do it. It's that you often can't do it very well, or you can't do it and live. Or you can't do it without an exorbitant amount of effort, money, or both.
Physics.
Yes, exactly. All right, so let's now go forward. Next step to think about is the sound barrier. There's a limit to how fast you can go, so to speak. It's not a limit, it's just a barrier, so if you can push through. Effectively, sound moves through air. And when you move faster, the sound is where you pile up and sort of make a large barrier of air in front of you. You can push through this with sufficient power, but the power required is a lot. In fact, actually, drag at supersonic at the sound barrier is stronger than it is when you go a bit above the sound barrier. There's actually a wall of pressure you have to overcome to cross the sound barrier. So pushing through the sound barrier becomes difficult, and you create a constant shockwave, so everything underneath you gets hit by a sonic boom. This can back break glass. A sonic boom can cause a lot of damage to the ground under the right or, for that matter, wrong conditions. So sonic booms happen, and they are not good. That's actually why, generally speaking, you can only make sonic booms over a limited range of territory. Over most of the continental U.S., you legally can't fly supersonic. I think the only place you can do it legally are some small stretches of land where the military has permission to do so, or the ocean, because it's the ocean.
Territorial waters are in mind.
I'm not going to go into the legal definitions, but generally speaking, over open international water, you can make a sonic boom.
So is that why the Concorde mainly has a
That why the Concorde mostly went,
to England and the United States or over the Atlantic.
partially, that was one of the reasons. The other reason was that it didn't have the range of the Pacific. The Concorde actually didn't have the range to go over the Pacific. It couldn't carry enough fuel to do that successfully.
And
The
it,
Concorde could only do the Atlantic safely. But yes, it was limited. It would usually do a climb, and then once it got over the ocean, it would afterburn itself up to super speed. But then it could actually turn off the afterburners and just do a super cruise without afterburner use. This is actually why it did better than the Soviet Concorde, the Tupolev Tu-144. That was attempted. They attempted to copy the Concorde, and it did not work out too well. It could fly, but it had some problems. It also crashed a few times. And also, if you flew it, it was super loud. You couldn't talk to the person next to you. It was so loud. People had to communicate by passing notes. It was a bad design. They copied all the Western tech, but didn't quite understand how it worked, so they got a bad knockoff. Anyway, that's neither here nor there. That's just a quick story about the Soviet attempts to copy the Concorde. It sort of worked. All right. Anyway, go fast, make sonic boom.
What about air?
Elaborate, please, on what your question is. What's your question?
Air travel?
Air travel? All commercial air travel is subsonic currently. Supersonic is not currently profitable. The Concorde had issues of filling seats because it was super expensive, and currently there's no commercially viable way of flying planes at that speed. It's generally cheaper and you can limit yourself to about 500 miles an hour. Below that, about that range, you have the sweet spot. You go too much faster, you can have significant transonic drag, and then the fuel costs go up astronomically. So we limit our planes to a certain speed because it's just cheaper. Put it this way, economic forces govern how fast we fly our planes.
they're developing a new supersonic, but it's still in testing.
Yes, exactly. There are new designs. They're currently testing. They're not commercially viable yet. They might be in the future. Currently, no. So let's fly a plane. Planes are nice. The ground doesn't get in the way, and we can now fly. But there's some problems. For one thing, simplest plane, propeller powered. The propellers only work up to about 90% the speed of sound. Why is that? Well, about 90% the speed of sound, the tips of your propeller occasionally crack the sound barrier. And once you crack the sound barrier, or get even close, the flow of air over the propeller starts to have spots where you develop shock waves from breaking the sound barrier. Remember, even if the tip is only going subsonic, some of the air gets fed up over the propeller. That's how wings work. And so you can break the sound barrier, which is not good because that suddenly means your wing doesn't work properly anymore. And suddenly you have a lot of drag, and your propeller is now dragging your plane backwards instead of pushing it forwards, which is bad.
So what comes up must come down.
So basically, if you start cracking the sound barrier, your plane has problems. Also, these wings don't work at supersonic speed. When you crack the sound barrier, the center of lift of an airplane slips backwards. So if you try and dive, you often can't pull back up out of it. Your plane wants to dive in supersonic flight. We discovered this during the first test of supersonic flight. They tried flying planes in steeper and steeper dives to break the sound barrier. Discovered that once you cross the sound barrier, you can't pull back up again, and your plane crashes. So yes, exactly. So they discovered a lot of ways you should not fly a plane. This was once again unintentional, but
Parachute on.
you can survive ejecting from a plane at supersonic speed. It's been done a few times. There's a case pilot was supersonic flying, and he had instrument failure meant his plane was diving into the ocean, so he bailed out at about 2,000 feet, and he did survive supersonic ejection from an airplane, but he was badly injured in the process, and his co-pilot died on ejection. So it can be done. It's not good. Also, the case of Bill Weaver, who was sometime around the development of the Blackbird, had his plane disintegrate at Mach 3.2 at 80,000 feet. His plane disintegrated around him, and he fell 80,000 feet. Luckily, his suit was blade around him, and he survived. His co-pilot, once again, did not survive. This was a Blackbird. That's a 71. U2 doesn't fly that fast. U2 only is limited to Mach 0.9, but can fly. Also can't fly 80,000. Only up to about 70,000. But yeah, Bill Weaver fell 80,000 feet. Basically, parachute took over. He landed in a ranch in Texas, and basically they learned how not to make a plane fly. They learned they used a test pilot for what became the Blackbird, and they discovered don't build the plane that way. It makes the plane disintegrate if you try turning. Which, if you have to turn the plane disintegrates, that's not a good plane. But so yes, you can survive ejecting a plane at supersonic speeds. No, you don't want to. Yes, you're likely to die. Yes, you can survive. Don't count on it. Hope that answers your question there. All right. So my point is, propeller planes only go so fast. They're limited to subsonic speeds, or they should be. Problem is, we did once upon a time build a supersonic propeller to the so-called Thunder Screech. This plane had a supersonic propeller. Why? What idiot would design this? Well, you see, they want, back in this day, jets couldn't generate instant power quickly. If you push the barrel of a jet, it'd take a while for it to catch. It was a problem with jets in the early days. So they said, what if we build a propeller in too, because they give you more power now? The problem is that we don't support our propeller. The propeller is constantly breaking the sound barrier. And that means it is the loudest plane ever built. They literally banned it from the airfield that they're supposed to be tested on because it was too loud. It caused the air traffic control tower to have windows break. It gave a guy a mechanic nearby a seizure. It literally, one test pilot said, there's not enough of you, you're not big enough to get me back in that plane. It was a horrible idea. It flew a few times, then we said, never again. It is the loudest airplane ever built. No, don't ever build it again. So yes, you can build a supersonic propeller. No, you should not. Yeah, bad idea, but hey, someone has to test it.
You can doesn't mean you don't.
Exactly. There's plenty of things you can do. You should not do them.
Yeah. Physics is the science of can you. The question of should you belongs in the realm of ethics, I think.
Something like that, yes. So let's go faster. Let's go even faster. We need a jet plane. You want to break the sound barrier? You need a jet. Well, jets are much more efficient and much faster, but they are hard to build and harder to fly. So let's cover how a jet plane actually does its stuff. Most jets we see are a commercial jet, which is what we call effectively a turbine engine. They use a turbine engine. Jets like you fly are usually a turbofan. We'll get to that in a moment. But a turbojet is actually a very simple concept. In front of the engine, you have a thing called a compressor. Air gets sucked in here. The compressor squeezes the air, heating it up greatly. It uses what we call a Rankine cycle in thermodynamics. Basically, squash the air gets really hot. You then dump some fuel in here. By dumping fuel in there, you then burn it, and then you get a lot of expansion. Expansion passes through a turbine, and then you get exhaust afterwards. This turbine spins the compressor, and you spit hot gas at the back of the engine. So basically, squash air, burn, add some fuel to burn it, spit the gas at the back, you go forwards. And generally speaking, you want to have as much compression here as possible, and you want to burn your fuel as efficient as possible here, get to the back. Your limit usually is how hot you can get this thing before this part of the engine melts. That's usually the limiting factor. What can you do before you melt the back of your engine off? And as you can guess, if part of your engine melts while in flight, that's not good. That's actually very bad. So usually the limiting factor is heat.
Pilots try to do.
It's usually pilots don't try. There's usually engineers try to squeeze more out, and then something doesn't work right. Usually test pilots tell them what doesn't work after they try it out and see what happens. There was, I believe, one Russian design where if you put the engine into full power, you couldn't take it out of full power at certain conditions because of the way the engine worked. So then they discovered the Americans tried to fly one once, and the pilot couldn't turn the engine off because the engine had a design flaw where once you got it going fast enough, it wouldn't stop going due to the way the engine handled not melting as a requirement. I don't have all the details of that one memorized, but there have been some attempts at engines that had some serious design flaws. So, effectively with a jet though, there's two philosophies that kind of make one work. One, push a lot of air out the back at a low speed. Push a bunch of air gradually. This is what most commercial jetliners use. You push more air slowly. Pushing it slowly is more efficient, but also it's slow. The other option is to push a little bit of air very, very fast. Get the air out the back, if that's possible, you push a little bit of it. That's good for supersonic flight. So, most jets use a turbofan. Basically, the jet engine right here, you bolt a giant fan on the front of it. Usually when as high a bypass as possible. Most of the air goes around the engine. The fan provides most of the thrust. Like for a 747 or a 737 or almost any jet plane you can imagine, the fan is most of the work. The engine mostly just drives that giant ducted fan. You should note that in general, these are very good, and the bigger the fan is, the more efficient it gets. However, the more drag you get too. There's a sweet spot of about 4 meters of fan diameter. Above about 4 meters, the drag outweighs the savings you get from extra thrust. So most of the time, the biggest you want to build is about 4 meters in diameter of fan. Above that, and the engine becomes inefficient due to drag reasons. Finally, this is why Boeing ended up building the ill-advised 737 MAX. They wanted a bigger engine so they had more efficiency, so they could fly further. The problem is they had done a to miss the ground, so put the engine higher in the plane, which destabilized the airframe. So they then made some computer hacks to fix that, which didn't work, and the plane started crashing. It was a whole, so literally trying to make the engine more efficient, broke the plane. And they didn't want to reuse on the plane because that's expensive. And Boeing took the philosophy of don't do it, just do it cheaply, don't do it well. And that of course caused the place of flying people to die. That was.
So they did have some problems.
Oh, they had a lot of issues, but once again, they chose to move away from do things well and right to do things cheap. And usually doing things cheaply is not always the best plan. Doing it cheaply often you're making trade-offs, and sometimes the trade-offs are worth it, sometimes the trade-offs are not worth it. My dad has a story where basically, apparently he tried buying the cheapest tires he could find on the market back in the 70s or 80s. And he discovered quickly that there's a reason you don't do that. The company had all the tires that blew out almost immediately, and the company went out of business for selling crap tires. But you know, if you buy cheap.
Why are you holding a bottle of water?
Does that answer your question? Okay, anyway. Fan jet works. Problem is, drag. You can't go too fast with a fan jet, so you need a turbofan. Problem is, they also have some issues. One thing is that, once again, you only put so much fuel in the air before the heat gets so strong your turbine begins to melt. So what do? Well, you dump the fuel into the afterburner section. Basically, you can dump some fuel into here and burn some of the exhaust. So there's still oxygen there after all, so you can burn it even more. Problem is, this is inefficient. You're basically dumping fuel back to your plane to make it go faster. Most military aircraft come with what we call an afterburner. These little things are designed to control the compression ratio or the expansion ratio of the gas. Effectively, when the gas gets to the back, depending on altitude, you might need different amounts of expansion to make the exhaust work properly. So these are able to adjust how much the gas expands in the back. The fire is the afterburner burning extra gas. These are great. They can help you break the sound barrier. The problem is you're basically dumping fuel at the back of your plane. So most planes only use the afterburner for a few seconds or a few minutes at a time before they have problems. Also, there's a few planes where they could hit Mach 3 briefly, but after you did so, you had to literally rebuild the afterburner and the whole engine because they're burning the engine out.
I think that's what the United States Air Force uses.
Most military crafts have some afterburners set up for going fast and for invasive maneuvers, but they're only used part-time. There's only a few planes in history that actually use afterburners for sustained flight. We'll talk about that one next, or soon, I should say. Basically, afterburners are great, but they're inefficient, and you're going to waste all your gas, and if you waste all your fuel tank going fast for a few seconds, that's not worth it. Okay, so what can go faster? Well, at some point, the problem is the fan in front of your engine stops being efficient, so instead, you want to use a ramjet. Best part about the ramjet? No moving parts. The ramjet relies on ram pressure. When you move forwards, air has to move out of your way. But at high speeds, air doesn't move very fast, so you get a compression shockwave in front of you. So the idea of the ramjet is this part right here, takes in air faster than the speed of sound. The motion forward compresses the air. And then you now have a pressure belt of your own forward motion. You then enter some fuel, burn it, and spin us back. Ramjet. Problem is, this only works if you're already moving above the speed of sound. They can provide thrust at low speeds. Thrust is usually not worth the cost of igniting it, but at supersonic speeds, these actually work pretty well. Around Mach 3, these work amazing. Problem is, you did Mach 3 first. So, details. So, in other words, you get compression forward motion, you have a ramjet, and it's very effective at flying you fast in general. Okay, that all works. Have you ever used these? Never alone. The closest we got to them is the Blackbird, which was not a ramjet. It was more of a turbojet with ramjet-like features. It was sort of a turbo ramjet, sort of. What happened was they had ram pressure in the engines, but then they bypassed some of that to the afterburner. So it functioned like both a turbojet and a ramjet at the same time at high speeds. And this is the only plane that I can think of that uses afterburner for more than an hour at a time. And it could go very fast, and it basically put it on at a high speed and high altitude. One problem was that basically its speed was not limited by anything like thrust. Every pilot that said no matter how fast you were going, the plane could go faster. They were not limited by thrust, they were limited by whether the airplane would melt. Literally. The limiting factor was, will the plane melt? Because at higher speeds, the back of your engine gets really hot. Eventually that back part starts to melt. If your engine melts, you don't have a plane anymore, you have a pump. So basically, they were limited by how hot the engine could get before it started to melt. Literally, they were limited by heat. Also, the plane was going so fast that the entire airframe could heat up a lot. So like if you touch the windshield with your fireproof gloves, your hands would start to get heated up by the windshield. And after they retemper the titanium of the frame every single flight. So literally, the metal got retempered every flight by the heat of flying. Furthermore, there was you couldn't seal the fuel tanks entirely due to the fact that of thermal expansion. So they simply built a tank so that it would leak a little bit on the ground. And then once you got to altitude and thrust, the tank would heat up and would seal better. They used a special fuel called JP7, which had a consistency of peanut butter. And it was also used as a heat sink. They duct heat into the fuel to keep everything cold before they burn it. It had a lot of interesting hacks to make things work. The problem was the fuel also wouldn't ignite. Like you could douse matches in the fuel that wouldn't ignite. Then you ignite with a thing called TEB or tetraboroethylene, a chemical that would spontaneously combust upon it introduced to air. It was highly carcinogenic, highly explosive. It was only going to make the fuel catch on fire. Yeah, this has a lot of hacks to make it work. They literally, you had to have special chemicals to light your fuel on fire. Otherwise, it wouldn't catch on fire. Like I said, design choices. But even then, this was limited to somewhere around Mach 3, around Mach 3.5, 3.6. We don't know how fast it could go. It could always go faster, but the problem is it would melt eventually, so that was a problem. Basically, it could sustain Mach 3.2, no problem. But going faster had issues. So once again, we're still limited to only about 3 times the speed of sound, which is, by and large, not that fast. Only about 2,000, a little over 2,000 miles an hour. So, not the best. Oh, it could. It can't run modern missiles, but it could not run missiles in the 80s and the 70s, but it could not run missiles today.
When are we going to reach rocket engines?
Later. In fact, we're going to reach rocket engines when I push this, when I don't push the next button, but the button after the next button, that's the next button. Does that answer your question? All right. Next up, we have a scramjet. What if you want to bypass the ramjet and go faster? You use a scramjet. Basically, at high speeds, the compression of the ramjet is non-viable. It's so compressive that the compression just doesn't work at a certain point. The ramming effect literally provides more drag than the thrust gives off. So instead, you make a scramjet. Scramjets work well above Mach 6 and possibly up to Mach 12. We're not certain how high they can go because we really haven't been able to test it very well. The problem is your fuel is burning in a supersonic airflow. It's like trying to keep a candle lit in a wind tunnel. You can do this. It's not easy. So the problem with a scramjet is keeping it lit is an issue. You literally have supersonic air burning in a combustion chamber. This is an issue. There are some tests. We've tested on missiles, but currently no place uses a scramjet. But it could work well above Mach 6. We've not tested this for a lot of reasons. Generally speaking, going that fast with the person on board seems to not have much in the way of benefits. You can't react fast to flight anyway. Almost every plane that's going to go faster is probably going to be just autonomous drone or something. People can't react fast enough at that speed. At high supersonic speeds, your reaction time is so slow. If there's a hazard coming, it's already embedded in your body by the time you recognize it's there. Bit of a problem. All right, so what if we go beyond that? What if we go to the next step? Well, scramjets only give you about Mach 12-ish. So what if we go beyond that? Well, then you need a rocket. Rockets are great. They work at all speeds. They even work in space. One problem. Basically a flying gas tank. If you look at this rocket here, almost everything you see in this picture is basically a gas tank. That whole big orange thing there, gas. And those things are solid fuel boosters. You basically burn fuel here, spit it out the back. You have the classic converging, diverging nozzle. Basically, the basic idea here is that you burn fuel in this chamber, the fuel burns, gets hot, around, and then you put your constriction. That constriction is like putting your finger over a hose. It speeds up the fuel. You get sped up to the boom, you get about the speed of sound, and then once you get to the speed of sound, you can't flow much faster than that normally. But since it's a gas, if you try going faster, the gas compresses a lot. So you have a choked flow. Choke the flow at the speed of sound here, then in this region, the fuel expands. When it expands, it cools off and speeds up significantly. So the geometry controls how much speed you get. By expanding out here, you now have fuel flow at the back of the engine at hypersonic speed, possibly, depending on how you set your geometry and how much pressure you have. So very effective. One problem: not only do you need to carry fuel, you need to carry your oxygen, the thing that makes your fuel burn. So you need to carry fuel and something to make the fuel actually burn. And carrying both is dangerous because the fuel oxygen mix, they tend to explode. A lot of rocket fuels are super nasty compounds. They're often smelly, carcinogenic, explosive, and toxic, and they have a few other problems too. They also are prone to burning uncontrollably. I remember reading a short passage from a book about a guy who was testing rocket fuel and rocket oxidizers back in the 60s. He mentioned that there's some of the fuels they had, you couldn't put them out once they started to burn. The only solution to them burning was to run away fast. They had one fuel where they spilled an oxidizer on a factory floor, and it lit the concrete on fire. The concrete was burning. then it burned the gravel too, below the concrete. It burned, and also by the way, that fire, at least the steam that came out of the fire, was hydrofluoric acid. Yeah, rocket fuel is no joke. Don't mess with rocket fuel. You can make some in your kitchen out of sugar. If you melt some sugar down the right way, you can make rocket fuel out of it. I'd recommend looking up online if you want to try this. Don't though, because if you do it wrong, your kitchen blows up.
All right, you do it outside.
Once again, if you put rocket fuel, you accept the risk that you might light yourself on fire a few times and possibly blow up. I don't like blowing up, so I don't do this.
You die.
I haven't died yet. I'm still here. Anyway, point is, rockets are great, but you need fuel oxidizer to make them run. And of course, you can power a plane with rockets. The most famous of these is the North American X-15, which held the absolute airspeed record. Basically, it was a jet-powered rocket. So it was a rocket-powered airplane. And the plane was designed to just test out rocket-powered flight. By the way, the engine of this plane only burned for 90 seconds. It had 90 seconds of gas, and then it would run out of fuel and it would glide to the ground. It tested out altitude and speed records. It had, and I think it's altitude records like 50 miles altitude. It's fly to space and have it coast back to the ground. Neil Armstrong was one of the test pilots for this one, testing out how it flew. Also holds the absolute airspeed record of Mach 6.7. And that's the absolute record for a manned flight. Why is no one broken that record yet? The plane nearly melted in the flight. You see, on that flight, Pete Knight got his flight up to Mach 6.7, and the plane's been inking out X, an alloy that holds it structurally at super high temperatures. At that speed, his airframe, with the blade of heat shield on it, still nearly melted in the flight. In fact, the entire plane had to be thrown away afterwards. The plane was so badly damaged with the flight, it couldn't fly again. This is the problem about like that. At that speed, the heat was so extreme, his plane basically melted around him, and he just barely avoided dying on, flight. But if you go to space, no air, so no air resistance. You just fly a rocket in space. Great. That's the idea. You can power a rocket-powered aircraft, and it works pretty well. So, what comes next? Well, basically, rockets are inefficient, and they use a lot of fuel, so is there a way you can cheat the system and get speed without using fuel? Of course you can. You do a thing called a gravity assist. If you were flying in space, you can bounce off planets to get gravity. You don't bounce off them literally, you bounce off their gravity. The basic idea is that from a planet's perspective, spacecraft comes in, swings around, and goes back out. The process is symmetric. Spacecraft comes in, swings around, and goes up symmetrically. However, planets are moving from the sun's perspective, so it's like bouncing off, say, the floor. It's like bouncing off of a baseball bat. It's a bit more gentle than that, obviously, but basically, planet goes on the planet, and boom, you get a speed boost from going around the planet. So if you aim your boost right, you can go faster. Question.
Like Skyhawk?
This is not Skyhawk. This is much better. This is a gravitational assist. You bounce on a planet's gravity to get a speed boost. You can do this many times. You don't have to do it. You can do this arbitrarily many times.
Skyhawks?
Say again, please.
Is this going to include Skyhawks?
No. Skyhooks are not good for getting speed. They're just good for getting yourself up. And currently we can't build Skyhooks.
It's been tested once.
Yet, I'm not going to touch Skyhooks. They're not good for going faster.
They're just getting up.
So anyway, this is good. You can do this many times. You can get a lot of speed this way. That's how the Parker Solar Probe got to the sun. They bounced off the gravity of I think Mars. I think was it Mars or either Mars or Jupiter several times, getting themselves closer to the sun incrementally. This is Mars. This is Mars, Venus, or Jupiter. I forget which one off the top of my head.
For which one?
Parker Solar Probe, was it Venus?
I want to say it was Venus.
Venus, that's what Venus.
Because they had or Venus and Mercury, because
Something like that.
They had
Anyway.
a weird loop-to-loop type thing going around to slow it down.
The gravitational assist from Earth.
Yeah, you can do a lot of gravity assists. The main point is to use them to get speed. The thing is, you can't get unlimited speed. You're limited to basically, you can't go too much faster than the planets themselves. You're limited by this basically. You can't get infinite speed. You can just get speed, and as you get faster, this process gets less and less efficient. This is good at getting a slow up and go fast. If you're already going fast, this gets less and less useful.
So it transfers the speed from the planet to the spacecraft, is that right?
Yeah, exactly.
Yeah.
You're borrowing planet speed. Voyager 2, by the way, did this thing where it bounced off each of the planet's gravity. It's set a 4-part bounce. It bounced off the first gravity of Jupiter, Saturn, Uranus, and Neptune all in sequence. Side note, this takes amazingly good aim. It's like throwing a dart at a dartboard and taking a bullseye 8,000 miles away. In this case, it was like hitting a bullseye, bouncing up the bullseye into the dartboard 8,000 miles further away, and do that 4 times. That's sort of what it's like. Or, if we use another metaphor, it's like taking a baseball in California, throwing it, and thinking about hitting a keyboard in New York City. Yeah, that takes good aim. Granted, they do adjust slightly, but the thing is, if your aim's off even a little bit, you miss the right key, which is kind of difficult. But you can still get out of the solar system very efficiently by bouncing off planetary gravity. So Voyager 2 did literally bounced off 4 planets in a row. It's a trick shot.
Think about they calculate all that out. Slide rule.
Oh yeah, you can calculate by hand if you want to. It's not fun. You can do that. The math is well understood. It's just it takes a lot. It's a lot of work.
Or you get Star Trek.
I can't with my head. Anyway, the main point is you still can't get unlimited speed. You're limited by the planets, and this only gets you going so fast. So let's go faster. Let's go faster than you can get using gravity assists. Let's now get the ion engine. Ion engines are amazing because instead of throwing fuel at the back of the rocket, a lot of fuel at the back, you throw out a tiny bit of fuel very, very quickly. Basically, you shoot out individual atoms at near light speed. Problem is,
Basically science fiction.
they work.
They have one.
We built these. The Dawn spacecraft went to Ceres using an ion engine. Literally, we've done this before. It's great. The problem is, your thrust is super low. Highly efficient, low fuel cost. Problem is, you can only use it in space because the thrust is so low. On Earth, it's not going to fly very well. It won't get out of the gravity because the thrust is so low. For reference, it's a bit like having a car that gets 1,000 miles to the gallon, efficiency-wise, but takes 4 days to go from 0 to 60. Yeah, I love the efficiency. I hate the acceleration. It takes you 4 days to go from 0 to 60. No. In space, if you're traveling for 6 months, that acceleration doesn't matter too much. You're just going to get there eventually. So that works. Great. Problem is, only in space, and still, you're limited by electrical power. So you need an electrical power supply. Dawn used solar panels. Massive solar panels. Yeah, I think they had 10 kilowatts of solar power to go, and they used only a few hundred kilograms of xenon to get themselves to Ceres, and I think Vesta as well. Basically, they did some cool work using an ion engine back to visit asteroids. They did a dwarf planets and asteroids. Worked pretty well. What about a solar sail? Light has momentum. You can bounce like your solar sail to go forwards. Problem is, and while this involves no fuel at all, this is an issue. We can't build an efficient sail that works at scale right now. To build a sail big enough to actually steer properly, you need a very light, strong material. Nothing we have currently works that's light enough and strong enough, and we can actually fabricate at scale. We can't make one that works. We can make micro solar sails. Problem is, we can't steer them. They've done some tests. Currently, the micro solar sails tumble uncontrollably. You can't steer yourself. And if you can fly in space but not steer, that's kind of useless. Question. The idea is you try and bounce the off your sail just the right way. Currently, this is all the solar sails are electronically controlled. They're all controlled by computer. It's not for it's just no. The limit is that literally with a small enough sail, it appears that there's no way to control it right now. We're working on that. There might be a way to control it eventually. So far, we haven't figured it out yet.
So how do you decelerate?
Once again, that's another problem. Question.
Most of these sound like they're from science fiction.
These are all real. We've built some of these small ones. There's a plan called Breakthrough Starshot. They plan to build a laser-powered solar sail to get yourself to Alpha Centauri in 20 years. Yeah, people have been testing this for a while. These are real things. You can totally do this. It's just, so far, we can't make them actually steer.
I mean, they're homo race, but no one else would.
I don't like these. Anyway, onward and forward. So solar sail is a great idea. They're still in the future. We might get these to work eventually, but it's not happening now. Maybe in 15, 20 years, we'll have some good solar sail-powered crafts, but not today, sadly. So let's go even further. What if we want to get to another star system now? What can we use? Well, I can only think of one method that actually function right now, and that is Project Orion, aka nuclear pulse propulsion. Basically, take a spaceship that's really heavy and drop thermonuclear bombs behind it to surf the shockwaves of the bombs. The sad part is this actually does work. This is a plan of Freeman Dyson. Literally, nuke yourself into orbit. He actually planned to build this at one point. Problem is, then there's a whole partial test ban treaty that made this illegal in the 60s. So now it's literally illegal to do this. Also, if you do this in Earth's magnetosphere, you might accidentally EMP the whole planet. We're not quite sure how far it will spread because we don't fully know how nukes handle EMPs properly, and no one wants to test out exactly how fast you could EMP the planet with a nuke right now for a lot of very good reasons. One of them being it's illegal.
No one wants to try it either.
Also, no one wants to see, could we destroy civilization? We don't want to see if the answer is yes. Question.
That's why it says literally everything else.
Yes. Yes. This has a lot of flaws, but it does technically work. They did some scale tests. You can look at some videos of scale tests in the 60s using chemical explosives to launch rockets. Literally bomb-powered rockets using C4 effectively. This does work. The problem is, you're literally nuking yourself into space. If anything goes wrong, you're very dead. You're literally nuked. So, yes, you can nuke yourself in orbit. You shouldn't. But this is currently the only thing I can think of that we could build with today's technology that would enable us to fly to the stars. Now, one problem you're going to run into with this, by the way, is also, once you're in space, surviving there is difficult. Currently, we can't build a biosphere that actually functions in a spaceship. If you want to go long distance, you need a self-contained biosphere that actually functions long-term without support. The space station only works if we keep on giving them food and other supplies, more or less constantly. Without constant resupply, the space station kind of literally dies. And so far, we've tried making closed biospheres that actually function, and the answer is that when we tried it, we discovered it doesn't work too well. Basically, we don't understand what you need to make a biosphere function entirely closed off. We think we know some things, but everything we've tried it doesn't work too well. Basically, ecosystems are hard to control. Building your own in the spaceship seems difficult. So, problems. But if we want to go to the stars, this would technically get us there. We might get there dead, but still, it would get us there.
Get our remains there.
And now let's do a few other things. Once you get to higher enough speed, you have to count for basic relativity. Effectively, at high speeds, everything gets kind of weird. From the perspective of everyone else, time runs slower to you. Lengths get contracted, light gets Doppler shifted, light gets beamed, and the energy required to go fast is just nonsensically, stupidly big. You do not want to see what the energy costs of going this fast. The energy costs are basically don't. And furthermore, we have an issue. At higher speeds, light gets Doppler shifted. So that means infrared light can get shifted in the ultraviolet and start cooking you with ultraviolet light. You can have ultraviolet get shifted in the X-ray. You get bombarded with X-rays from just the Doppler shifting of all the light around you. Also get beams. Moving towards it, it gets brighter. Light literally changes its wavelength as you move around, and that can cause problems. You can literally cook yourself with the wrong light, shifting it around the wrong way. It would not go well for you. Basically, relativity causes problems as you go fast. For example, at high speed, you have some problems. This is an example of speed damage. This is a window from the International Space Station. It was struck by a fleck of paint a few thousandths of an inch across, and it cracked the window. The fleck of paint was moving only 17,000 miles an hour. Only. For reference, relativity kicks in around 60 million miles an hour. Speed of light is, by the way, 667 million miles an hour, so around 1/10 light speed, relativity is important. So at about 60 million miles an hour, relativity is a problem. Note, this number is bigger. At relative speeds, every collision carries the energy of a nuclear bomb. Like, there's a fun example on XKC's What If page about what would happen if you pitch a baseball at 90% light speed. Answer, you basically nuke everyone. The kinetic energy of the rate of the baseball is the equivalent to a thermonuclear bomb. So a baseball pitched at that speed would blow up. Also, it would cause a lot of other problems too. And, at that speed, even a collision with an atom is dangerous. If you hit a hydrogen atom at relative speeds, it gives off X-rays. The X-rays that you're going to irradiate yourself. Radiation causes problems, like cancer, and radiation sickness, and other problems too. So in other words, at higher speeds, even hitting a hydrogen atom can start to give you cancer. And that's not desirable. So in other words, at high speeds, we might just irradiate ourselves to death quickly. Also, how do you stop? How are you going to stop? And so that's another problem. To stop, you need to something you use energy in reverse, and that's another big issue. So could you stop? We don't know how to yet. And so on. Now, how can we go faster? Well, currently the fastest known fastest known particles with actual mass are charged particles called cosmic rays. Light can go faster, yes, but you can't actually become light yourself. Or if you did, you wouldn't be a person anymore. So, fastest particles that we know of that are not just light are cosmic rays. They go very fast. A lot of them are accelerated by shock waves. When you have an explosion, you can get shock waves between bits of gas moving around. Bouncing around a shock wave can accelerate to basically 99.99999% the speed of light. This is how many cosmic rays are accelerated. Shock wave happens, particles get accelerated. Exactly how we're still working out, but we know that shock waves can accelerate particles to absurd speeds. So can we start a shock wave to high speed? Theoretically, but it probably would kill us instantaneously. So maybe we shouldn't try this one. It gets going fast, but it'll probably instantaneous death. Also, one thing in giant powerful shock waves are basically supernovas and collapse arcs, which if you're doing a supernova, everything can kill you. Literally, everything about it can kill you. So don't. Perhaps. Like, the energy you lose to the gamma ray burst would cook the entire planet in a fraction of a second. It's not nothing to scoff at. So basically, not the best plan. Not vapor as a planet. You could at least amount all life in the planet with this. That's just be for a small one. They get bigger.
Gamma ray burst.
Yeah, GRBs. They get bigger. I think also some galaxies kick out just a permanent jet of this. Like the strongest known quasar is 3C273. Its jet currently has the luminosity of 4 trillion suns. Just constant beam of 4 trillion suns in a jet, pointed somewhat near us. It's far away, we're fine. If it was close to us, we'd be dead. So clearly it's not close to us.
What's the name of it?
3C273. It's currently the most luminous quasar we know. It has luminosity of about 4 trillion suns. Roughly, I'm rounding here. But thing is, even this is limited light speed. So how do you go faster? Well, currently there's no way to break the speed of light, but there is a way to bypass it, sort of. One cool idea is the Albuquerque drive, where you basically fold space. You basically, if you warp space in front and behind you, you can create a bubble that could theoretically slide through space faster than light. Problem is, well, the theories that you can do this, actually practically is not understood, like at all. Currently, the Albuquerque, we didn't teleport an atom. That's an inaccurate description. It wasn't quite teleportation. Anyway, this one here would require negative mass. So the Albuquerque drive basically involves folding space, and currently we have no idea how to do this. Now, the theory says it could work. Problem is, some things are theoretically possible, but not actually practically possible. And all methods say this might require negative mass to work, or worse, imaginary mass. And we can't make negative mass, and imaginary mass flat out doesn't exist.
Einstein-Rosen bridges.
We're not. That involves, that's once again folding space, and that would require negative mass.
Fahrenheit string theory, wormholes, can't wormholes, whatever wormholes.
I think you're just saying words now.
Okay.
They are real things. Those are all real things, but those are not going to help us. And also, again, all of them would require things we don't know how to make, or if we did make them, possibly would probably self-destruct instantaneously, which, once again, not useful. We know that wormholes could theoretically exist. The problem is all our mass suggests that if you make one, it probably would collapse instantly without negative mass, and that's a problem. And if you did make one, it still might also blow up. We don't know the math perfectly. The math also, their existence might only be an artifact of relativity. It's like a solution that gives you an imaginary answer for a perfect equation. It's useful in a lot of situations, but it's not good at physical answer. If it tells you that the time is imaginary, it means it didn't happen, not that it was imaginary. So sometimes imaginary answer just means the math works, but the physical interpretation isn't real. One of those problems. So I think we'll stop here. Limit. This is about the limit of what you can do speed-wise, and once again, this might not be even possible. So that's a bit about going fast. As you can guess, we can do a lot of things, but some of them might not work too well. Some of them might involve dying horribly. So who has more questions of doom, despair, or fish?
So you're saying reality is what's keeping us limited in terms of where we can go in space?
Yes, reality is definitely the biggest limit. We could go faster in theory, but so far nothing actually seems to function properly that way. And while some are really cool, once again, we have no idea how to actually achieve that in practice. And while there are some people that claim there's teleportation, it's more quirks of the way we're handling quantum mechanics, and that still doesn't actually teleport anything, and it still doesn't bind locality. So far, no theory has ever been able to break causality or locality. We have never been able to break light speed in a practical sense. We've been able to make some things do weird stuff, but we can't access information faster than light anywhere. We've tried a lot. We have been trying so hard. The answer is so far, you can't.
How badly would things mess up if we did start sending things through faster than light? Like, how many theories would we have to rethink?
We have to rethink a lot of theories, including relativity, which is well tested. We have to rethink almost all of our theories. So far, also, there might be ways to break light speed without breaking the theories entirely, but they lead to issues of possible time travel. So, right now, the basic theory is that we assume it's impossible, but there are ways of working right if it is possible, and so far, if they violate causality, then we have no idea what's going on. So far, we can't violate causality. We've tried hard. We've tried to break causality. So far, the answer is you can't. But we're still trying, just in case you can. Yes, there's been trying to break causality. They've all failed. Duh. I'm not very familiar with that. I'd have to look that one up. I am not familiar with that. That was likely that's a theoretical paper, and that's one of those where they're posing some new theories but until they actually have some evidence to support that theory or that hypothesis, there's not a lot we could go on. And I think the theory probably does make sense at some level, but it might just not. It might be one of those cases where the theory makes sense but isn't actually correct. Like when I was in graduate school, we did a problem where we showed that a method for modeling how water would freeze if space was four-dimensional. The math worked perfectly, but space doesn't have four spatial dimensions. Ergo, the model for how water freezes in 4 dimensions doesn't actually work. The model makes sense, it just doesn't describe our reality. So that paper might also be describing a theoretically possible reality, just not the one we live in. To my knowledge, there's currently no evidence for something like that, but that might change with more experimentation. Other questions?
Yeah, I got one about relativity. So
Go ahead.
You can't travel the speed of light. You can travel, let's say, 3/4.
Totally. You can to use a math term, you can get asymptotically close to light speed.
So if you're traveling 3/4 speed of light, positive direction.
Mhm.
He's traveling through, someone else is traveling 3/4 speed of light in the negative direction. The observer is moving in the positive direction, observing the person in the negative
Ah.
direction.
This is where we hit a big problem. Speeds don't add linearly. To us, if I go 2 that way and someone else goes 2 that way, we're seeing each other move away from each other at 4. But at relativity, that common sense understanding breaks completely. As in, speeds don't add linearly when they're relativistic. At relativistic speeds, they add differently. There's some correction factors to speed addition at relativistic speeds. I can pull up the math for it if you really want me to, but the math just basically says that actually you have to modify the way you add speeds together by relativistic factors, and that makes that go away. There will be time differences, yes. I have to pull up my notes on how this works. It's something you cover in a general introduction to relativity class. That situation is actually more like the textbook case for why that doesn't break speed of light. You can go over the math. Essentially, there's a way of doing a force-based transition where you effectively boost your speed in a matrix. I don't want to dive into the math very deeply. It's wildly strange.
The faster you go, time slows down.
No, the faster you go away, the more time goes back.
More specifically, the faster you go, time slows from someone else's perspective. So I would feel time going normally, but actually, someone outside my spaceship would see time going slower for me specifically. Similarly, I see their time going slower too.
So if you left the Earth at light speed, 15 minutes on the other side of the galaxy.
Yep.
Come back a million years faster.
Yep.
30 minutes your time.
Yep, exactly. That's totally real stuff. Completely real physics. That would totally work. You'd have to be going stupidly fast, but yes, that is totally possible.
I think don't they have to account for relativity with the speed of satellites to get the
There's time travel like a few seconds into the future.
Yeah, you can go forwards. You can go forwards. Yeah, so far, going back in the time doesn't work. Going forwards, that's easy. We're doing it right now. We're traveling through time 1 second per second. But can't go back. You can go faster locally by just adjusting relativity. You wouldn't actually live longer. You wouldn't actually skip the time. You'd simply experience it at a different rate. So relativity does not let you travel through time. It just lets you experience time at a slightly different pace. But once again, you wouldn't actually live longer. You just see time would be different for you temporarily.
Can you say that one more time? If you go the speed of light, you'd be across the galaxy how long?
You'd perceive time differently. As you go faster, you could perceive time at a slower pace. So your trip would happen much faster than it would for someone outside your ship. So while your trip would take millions of years, or 100,000 years from our perspective, if you were in the ship, it would be a short period of time because of the way relativity functions. Time slows down for the person traveling. Once again, math of relativity gets interesting. If you really want me to dive into the math of it, I can break that. I can get my notes and break out the math of relativity. I can tell you the math gets complicated quickly and is not very satisfying.
Yeah, there's one other line.
And the warp drive, everything's about theory only.
Theory only. No one knows how to do this. No, it might not even be possible. The theory says it could happen. That theory might be wrong.
One other question. You mentioned if something's traveling at the speed of light and it impacts another object that's not traveling.
Or even trying to build AI period.
So if let's say I've got a baseball and throw it at you at the speed of light, the amount of time that all the baseball and you are occupying the same space is extremely small.
Very small.
Very small that the particles inside the atom are almost motionless.
Almost.
At that time.
Yep.
And an atom is mostly empty space.
Yep.
So the probability that they'll actually impact.
The problem you're forgetting, they're small physically, but when particles collide, the particles themselves aren't touching. Their electric fields are colliding. The electric fields extend well beyond the atom. So when two atoms collide, they're not actually touching. Their electric fields are interacting.
So if you get to a point
No.
fast enough
No.
so where they wouldn't interact.
Electric fields interact at light speed. So no, you can't get fast enough for that to happen. That doesn't work. Sadly, no. The answer is that it basically would be like each collision with an atom would basically be like a small nuclear explosion. Yeah.
What about if you throw in quantum probability?
I'm not going to deal with that. Put it this way. Actually, no, I will deal with that. If you do quantum tunneling, the probability is so low that if you try quantum tunneling through a wall, every second for 13 billion years, you still have better odds of winning every single lottery tomorrow. Yes.
So you're saying
of winning every single lottery tomorrow, from right now, by buying all the perfect tickets, your odds of winning every single lottery tomorrow are better than the probability of tunneling through a wall by walking to it once per second for 13 billion years.
So you're saying it's possible?
Oh, it's totally possible. It's just never going to happen. It's one of those where it's like I think you have to do it like 10 to the 10 to the 10 to the 120 times, which is yes, it's a real number. No, it's not a number that's going to happen. It's like pointing out that the universe will experience heat death in like 10 to the 10 to the 120 years. That's when absolute heat death is supposed to happen. That's so far in the future. If you measure it in seconds or millennia, it's the same answer.
What about gravitational influences when we're talking these speeds?
They wouldn't be relevant, but the speeds of the speeds of light, a black hole to get some energy out of the rotation. But that still doesn't actually let you break the speed of light or anything else. It just lets you extract some mass energy from a black hole indirectly by the fact that it drags space with it as it spins. So yes, you can do some tricks with black holes. No, they don't actually break anything like the speed of light.
Just the rest of physics.
They break some things, but they don't break any doesn't break any physical theory that we actually have worked out. No, it doesn't escape. Black holes have a temperature, so they actually give off radiation in the form of Hawking radiation, but that's not coming out of the black hole. It's coming out of the space around the black hole. The net effect of the black hole does lose mass through Hawking radiation, but the radiation doesn't come from the whole itself. It comes from a region of space around the black hole. In fact, every single object technically does Hawking radiation. It's just that if you're not a black hole, the effect is so negligible it's not worth talking about. Black holes give off Hawking radiation. The bigger the number, the weaker the radiation is. So like black holes actually give off Hawking radiation significantly. Like if a black hole is less than the mass of the moon, the Hawking radiation coming off it is actually stronger than the CMB it takes in. So black holes lighter than the moon would actually start evaporating faster than they grow, just from that. So if I make this water bubble a black hole right now, it would quickly become a nuclear explosion as it radiates all energy off into space instantaneously. It would be a nuclear bomb. Whereas if I made one that's the mass of the moon, it would actually survive temporarily. Then the mass of the Earth, it would survive a while as well. But generally speaking, bigger black holes give off less radiation that way. All black holes that are known to exist currently are so cold we can't detect the radiation directly. They're colder than the CMB. And the CMB and that means the CMB drowns it out. Therefore, you can't see it. So yes, black holes give off radiation. No, you're not gonna see any of that. We've only ever been able to see that happen directly through things like analog testing, where we test like ripples in water as a model. So far, you can't test Hawking radiation directly for a lot of reasons. One of them being it's too weak.
And there's only one official picture of a black hole.
Say again, please.
And there's only one official picture of a black hole.
There's a few pictures. There's at least two from the Event Horizon Telescope. We got one of M73, no, M76. I forget the exact number. And 80. That's the one. And also the black hole center of our galaxy. So there's those two. There's the M87. That's right. And Sag star. So they've taken both those, but those are pictures. Those aren't the Event Horizon. Those are the accretion disk around the Event Horizon in radio images. So the radio image of the accretion around the black hole central area. You can't see the Event Horizon. You can see the light orbiting the black hole and the material orbiting the black hole. So you're seeing the accretion disk, not the actual black hole. The black hole itself looks black. If you look at the YouTube channel there, Cassian, he's a very good explanation of how the picture formed and why it looks the way it does.
So, universe is constantly expanding.
Yes, it is.
So, is there any, in theory, if you get to a state in theory, you can get to the point where you catch the attention?
With this, the answer is maybe, but we don't know.
You don't know.
We don't know.
With the warp drive, you might, maybe.
The answer is we don't know, and if maybe, we don't know.
Last thing I read said that you would never get to the end.
Yeah, that is true. You didn't get the end, but you might be able to get past the light horizon we're used to, but that's theoretical at best. And we just don't know what would happen if you actually did this. The answer is maybe, but there'd never be an end. You'd never hit the end of the universe. You can get to what we can see right now, but beyond that, there'd just be more stuff we can't currently see.
If the end of the universe we see right now,
it's gonna keep expanding.
Yeah.
You're traveling it, so
Right.
you say you're never
You'll
going
never
to
get, you end up.
It's
Right.
possible that there is an edge somewhere, but currently we don't have any reason to expect there should be.
Okay.
And it's also untested. So if there is an edge, we can't observe it, and even if we could, we could never observe it. So
But you know how fast the thing is expanding here, right?
no, the problem is there could be stuff beyond that we can see.
But isn't it expanding in the same direction from any point that you
Yes,
take in
also
the
the
universe?
expansion is isotropic, so that means wherever you are, expansion is away from you at all points. So no matter where you go, expansion is uniform away from you. It's not, there's no center of expansion. The expansion is uniform everywhere, which is a problem. So suffice to say that we don't expect to ever see an edge. That could be wrong, but we have no reason to suspect that, and we don't know. We just don't have any reason to suspect there should be. Yeah, space is weird.
Yeah.
Believe me, we're looking into more about why expansion works the way it does. There's gonna be some more insights into dark energy probably in the next decade or two, where there's some experiments that are probing into why dark energy functions the way it does. They might give us some answers in the next 10, 15 years, but they also might just show that we have no idea what's going on yet. That's the thing with research, don't know what you're gonna get.
Which is exciting.
Yes, I'm looking forward to some of the results we're going to get. Webb is currently throwing some new insights into the way expansion happens. So far, it's simply increased the Hubble tension, the idea that we don't understand how space is expanding at all. It's definitely increasing the idea that there's something wrong. We just don't know what. It just gives us more sense that yes, something's definitely wrong somewhere. What's wrong? We're not really sure. We'd like to find out. We'd love to find out. We just don't know. And maybe it'll help find out. Maybe it'll just tell us that we need to look somewhere else. Unknown. Yeah. But this way, if we knew the answer, we wouldn't have built Webb. There's a few bits of it. The main reason for dark energy, the idea of dark energy is that it is mass all throughout space. We know dark matter, so we can see stuff orbiting invisible mass. Basically. We can see this mass we can't see, stuff orbiting it. We can track dark matter by orbits. For example, there's currently about 1 squirrel worth of dark matter inside Earth. You can map it mathematically. We're about 4 bananas of dark matter inside Earth. Anyway, dark energy is a different beast. We don't. That's happened because we observe. If you look at the amount of matter, both dark and luminous, present in the universe, it adds up to about 27% of the amount of mass you need for the universe to be the shape it is right now. You need more mass for the universe to be flat, observationally. The universe looks flat to all our observations. If the universe was actually the mass that we see, it would be effectively hyperbolic. We'd have hyperbolic space. Space isn't hyperbolic, so that is a problem. Ergo, there must be mass we can't see and does not clump up at all. Dark matter does clump up around galaxies. It's just not there in the void. The voids are lacking dark matter. The parts where we live have more dark matter. Ergo, and galaxies have dark matter halos that are concentrated around the galaxy. So, dark energy, there must be something in space that does not clump up anywhere and has mass and somehow makes space do things. That means there must be energy out there. That's the idea for dark energy. It's essentially a thing we said to make space the right shape. Because there's matter we can't see, it's not clumping up, and it seems to be everywhere, uniformly, and the only thing it's going to do is make space expand faster. As for how it functions or what it even is, your guess is as good as mine. We just literally have no idea. We'd love to know more. So far, the answer is we got nothing. All the problems that dark energy is going to detect the effects of acceleration will be felt over distances on the order of galaxy clusters. You only know because on the scale of galaxies and galaxy clusters, the cluster has enough gravity to overcome dark energy. But if you're going inside between superclusters, that's the space where you actually can see dark energy making galaxies expand fast, accelerate. You have to go between superclusters. That's the scale we're talking about. Like, it has to be in the mega or gigaparsec scale to really be apparent. That's the scale we're talking about for dark energy to be relevant. Gigaparsecs. Yeah, that's a lot.
Okay, well, thank you very much for the next presentation. Just take about a 5-minute break. People, there's coffee, cookies, looks like a cake or something over there.